Hello and Assalamualaikum. Today we're going to talk about the assignment power factor correction in AC circuit. Yes, our members, we have Teo Yun Chai, Ong Chezwan, and me, Muhammad Firaswai bin Karunizam. So what's the table contents that we have here are introduction, objective, simulation, comparison data and result, theoretical and simulation, discussion and conclusion. For my part, I will do the introduction and the objective. So we have a two circuit here, which is ACRL parallel circuit. As we know, R for the resistor, L for the inductor, and it was in parallel. So the current and the voltage are outphased due to the inductive reactance. So while RLC parallel circuit, which is consists R for resistor, L for inductor, C for capacitor, and parallel, which is the circuit design which is in parallel. So another thing is we have a power factor. Power factor measure how efficient electrical power is used as a ratio real power to apparent power. In resistive circuit, power factor is equals to 1, which means voltage and current are in phase. In inductive or capacitive circuit, power factor below 1, voltage and current are out of phase. So here's our objective. Firstly, we design and simulate. Create the parallel AC circuit using multisim, which and a AC supply resistor, inductor, and capacitor. Power factor correction. Apply the power factor correction by adjusting the capacitor to improve the circuit power factor. Record and compare. We measure and compare the circuit performance before and after power factor correction, focusing on current, voltage, and phase angle. Circuit functionality is to ensure the circuit run correctly and demonstrate the impact of the power factor correction and on efficiency and reactive power. The next part, my member will talk about it. All right.
Hi, I'm Winchai. I would like to present the simulation part. For the design of the circuit, before power factor corrections, a 20 ohm resistor is connected in parallel with a 100 mH inductor across a 230 volt 50 Hz AC supply. First, the value of the current supply is measured by a multimeter in simulation and it gets 30.62 ampere. For the power is get 2.645 kilowatt. The power factor is 0.84435. Beside that, for the current across resistor is 11.5 amperes and current across the inductor is 7.298 amperes. Next, using the oscilloscope to get the voltage current graph. In this graph, we can see the current is lagging voltage. Furthermore, to let the power factor corrected, we need to add a capacitor to cancel the inductive reactance. In order to find the capacitance values, first of all we need to make an inductive reactance equal to the capacitive reactance. Therefore, the capacitor value is 101.3 microfarad by solving calculation. Next is the circuit design after the power factor corrections. A 20 ohms resistor, a 100 mH inductor, and 103 microfarad capacitor connected in parallel with a 230 volt and 50 Hz AC supply. The simulation for current supply is 11.5 amperes. After the power factor correction, the value of power is 2.645 kilowatts. The power factor is 0.9999, nearly to 1, which is unity. In addition, for current across the resistor is 11.5 ampere. Current across the inductor is 7.298 amperes and current across the capacitor is 7.343 amperes. Next, the voltage current graph by using the oscilloscope. In this graph, we can see the current and voltage are in phase. It shows that the angular displacement is 0, so the power factor is equal to 1, where the power factor is cos theta and cos 0 is equal to 1. Next, the data result in theory and simulation are compared. Before the power factor correction, the theoretical power value and the simulation power value are the same, both of which are 2.645 kW. Secondly, the theoretical power factor is 0.84359 and the simulation power factor is 0.84435. Next, the current supply in theory is 13.63 ampere and in simulation is 30.62 ampere. For the current across the resistor is 11.5 in theory and simulation. The current across the inductor is 7.32 ampere in theory and 7.298 ampere in simulations. Next is the result after power factor correction. The value of power is the same in theory and simulation, which is 2.645 kW. The value of power factor is 1 in theory and 0.99999 in simulations. In addition, the power supply current and the current across the resistor are the same, both of which are 11.5 ampere. For the value of current inductor is 7.32 amperes in theory and 7.298 ampere in simulation. Lastly, for the current across the capacitor, the theoretical value is 7.32 ampere and the simulation value is 7.343 amperes.
Hello, this is Sean here. Now we go to the discussion. Firstly, importance of power factor correction. A low power factor indicates inefficiency in the circuit due to high reactive power. So, poor power factor increases the current flow for a given power level, leading to higher energy losses in transmission line and transformers. Next, causes of low power factor, like inductive load and unbalanced load. What the difference between the both of the loads are inductive loads are devices such as motor, but unbalanced load are the unequal load distribution can cause further reduction in the power factor, means that the unbalanced load in the motor or with the circuit that we construct. Last, we go to the benefit of power factor correction, which is reduce energy losses, lowers electricity bills, enhance voltage stability in the system, and frees up capacity in transformer and distribution lines. Now we go to the conclusion. Power factor correction is an essential practice in AC electrical system to enhance energy efficiency, reduce costs, and improve system reliability. The selection of correction method depends on the type of load, system size, and economic consideration. However, capacitor banks are the most widely used solution due to their simplicity and cost-effectiveness. However, advanced systems like HVC may be required for dynamic compensation in industrial settings. There is there are not many methods of power factor correction, but capacitor banks are the most efficiency and most widely used in the all industrial. Thus, to achieve optimal power factor, it is critical to analyze the system load profile and integrate a balanced approach to correction. Regular maintenance and monitoring of correction equipment ensure sustained benefits and potential system issues like overcompensation or harmonic distortion. This means that the optimal power factor is not easy to achieve. So we need to analyze the system of the load profile or others issue like balancing the load and so on. So we need choose the most suitable method to achieve the optimum power factor by power factor correction. That's all from us.